Hello everyone, welcome to CSCE 317, Lecture 11. So we are entering our final week of class. Today I'll give a brief lecture where I make some announcements and then talk about Lab 4, Quiz 4, and the final exam. So the Lab 4 will be assigning today. It'll be due on reading day, which is 1 week from today. We want to remind you that the labs, the 4 labs, according to the updated syllabus, will carry weights of 10, 15, 15, and 20% respectively. So this lab will have a weight of 20%. Quiz 4 will be assigned tomorrow. It'll be due on Friday. And the quizzes individually will have a weight of 5%. And then the final exam we will assign on Dropbox. It'll be up on the normal exam time on May 4th from 12:30 to 3 o'clock, and it'll carry a weight of 20%. Next Monday, I will post a lecture that will review the material for the final exam and provide more details of that. So hopefully you were able to watch the last lecture where I talked about I²C. I will, to briefly summarize, it is a 2-wire interface. It is comprised of the wires are SDA, which stands for serial data, and SCL, which stands for serial clock. The wires are both shared by all of the devices that are connected to the bus. And so, and it is a multi-master bus, meaning that any device can take mastership of the bus. And so the technology is set up to where any device on the bus is able to drive both of the signals or read both of the signals. So SDA and SCL are essentially input-output pins with respect to every device that is connected to the bus. So this introduces the idea that there are 4 types of transactions. There is from the perspective of a device on the bus, I can perform a master read or master write to any other device on the bus, or I might also have to act like a slave if another device on the bus wishes to read or write to me. So there are 4 types of transactions. There's a master read, a master write, a slave read, and a slave write. And of course, the read and write are similar to what we had with SPI, where you've got an address and data associated with a read or write transaction. So for example, I could perform a master read on another device, or another device may perform a slave write to me. In either one of those cases, one word of data would be sent from that other device to me. Okay. So this slide contains 6 what I consider to be sort of the main points of I²C, the most important 9 facts about I²C. Each transaction, I²C transaction, contains, at least the ones that we use that we're using in this class, they contain, sorry, typo there. They contain an address phase, where the address is conveyed, and a data phase where the data phase is conveyed. The address and the data phase both comprise 9 bits or 9-bit slots, or 9 clock cycles, where there's 1 bit conveyed per clock cycle. So there's an address phase and a data phase. The address phase comes before the data phase. Now this is assuming that you're only transacting 1 byte, and in fact there is a way you can transact more than 1 byte with I²C, much like we did with SPI in the last lab, but we are not going to cover that type of transaction this semester. So we are focusing only on the single byte transactions. The master, whoever is the master in each transaction, and by the way, each transaction has has a master and a slave, and you can't change roles within one transaction. So for each transaction, one device is always the master throughout that transaction, and another device is always the slave. The master will always control the clock. So that's pretty straightforward. The tricky part, though, is that the data line, the SDA, will change control throughout the transaction. So during a transaction, the SDA will be output by one device and input into another, but the device that's outputting and the device that's inputting will flip a few times during the transaction. That's the part that's kind of, I think, is the most tricky thing to understand here. So for a write operation, a write transaction, the master will control SDA initially when the transaction starts, and it will use it to send 8 bits of address during the address phase. Also, it will control SDA to send the byte to the slave, because it's a write, during the data phase. However, the slave will take control of SDA for the 9th bit, or the 9th cycle of the address phase, as well as the 9th bit or the 9th cycle of the data phase, in order to acknowledge the master, in order to acknowledge the address and also the data. So in other words, during a write transaction, the master controls the SDA line for 16 cycles, and the slave controls it for 2 cycles. And for a read operation, the master controls the SDA for 8 cycles of the address phase, as before, but it yields control over the SDA for the 8 cycles of the data during the data phase, but then the master is in charge of the acknowledgement. So in other words, the master controls SDA for 8 cycles during the address phase and 1 cycle of the data phase for the read operation. And then likewise, the slave controls SDA for 1 cycle of the address phase and 8 cycles of the data phase. So that part is, like I said, that part is kind of tricky, because you have this handover of control. Like if I do a transaction, I'm the master, I toggle SDA for 8 cycles, and then I give up control of SDA for only 1 cycle, so the slave can use it to acknowledge me, and then I take back control again if I'm doing a write, for instance. So that part is, wanted to make that part clear. The other part I think that's a little tricky is the start bit and the stop bit. The master, being the one that initiates the transaction, has to send a start bit and has to send a stop bit that marks the beginning and end of a transaction. So that part is pretty straightforward, but the way that happens is a little strange, because the start bit and the stop bit it's kind of a misnomer, because they're not really bits. What they are edges. So the start bit is the falling edge of SDA while the SCL is high, and the stop bit is the rising edge of SDA while SCL is high. So that part is a little confusing, especially considering that they call it the start bit and the stop bit, and there are actual bits, sort of proper bits that are sent during the address and data phase and the acknowledgement. Those are actual bits in the sense that they are asserted for a whole clock cycle, whereas the start and stop bit are not asserted for a clock cycle necessarily. They're really just transitions of SDA. So now if you can understand those 6 bullet points, then you likely have a very thorough understanding of I squared C. Okay, so Lab 4 is due in a week, so we tried to make it, we tried to limit the amount of workload associated with it, so you should be able to finish it fairly quickly. One of the ways we did that was we essentially made the overall objective the same as in Lab 3. The setup and the environment is the same. So you have a simulated CPU, and then you have a sensor, which we call now VD004, and a storage device that we call VD005. All three of these devices are connected to an I2C bus, and the objective is for the sensor is really for the CPU to act as a bridge to convey sensor readings from the sensor and store them in the storage device, and then that's it. So the premise is that you've got like some sort of sensor, like a temperature sensor that you put out in the field, and it basically just collects data. You've got a CPU that conveys this data from the sensor to the storage device, and then just leaves it there. And then at some point in the future, someone will come around and take the storage device and read it in some other environment. So, but basically just sensor data being sent over, being stored in a storage device. The CPU is acting really as just a conveyor belt. There's a few differences though from Lab 3. The main ones are that we're using I2C instead of SPI. So obviously the objective here is to convert the SPI bus to an I2C bus. As I mentioned in a few minutes ago, I2C does have the ability to send more than one byte in a transaction. In the previous lab, we called it streaming mode, but with I2C, it's called combined transactions. We are not going to cover combined I2C transactions in this semester. We're just not going to get to it. So all of the transactions performed in Lab 4 will be single word transaction. There'll be no streams. The other difference is that we are going to simplify the storage device interface. Now there is no need to write the offset of each byte that you're going to write to the storage device, as there was in the last lab. We're going to assume that you can just write consecutive bytes into the data register on the storage device, and then the storage device will keep track of the offset. It'll increment the offset automatically. So that will be, instead of having to always write the offset and then the data, you only have to write the data register for the storage device. There will still be a page number that you have to set. And so what happens internally is every time the CPU writes the page number for the storage device, it will reset the offset internally to 0. So every time you change pages and then you start writing into the page, you'll begin writing at the beginning of the page. And that offset counter is internal. The VD004, the sensor, and this is probably the biggest change, the sensor will be sending its data to the CPU using master write transactions. So what that means is that the CPU will be receiving sensor data from the sensor at whenever the sensor wants to send it, as opposed to the last lab where the CPU had to pull the sensor data and pull sensor values out actively. Now, with respect to reading sensor values, the CPU is more of a passive participant, where it receives sensor data through as a slave, and so it's being force-fed sort of the sensor values from the sensor. The sensor will become the master, and it will write the sensor values into the CPU, where the CPU is acting like a slave. So there's no the CPU won't have control over when it receives sensor values. The way that we have it set up is that when the CPU reads the number of pages that are available in the storage device, that will trigger the sensor to start sending its data to the CPU, and it will do so whenever it's been idle, whenever the sensor's been idle for 200 clock cycles. So basically, every 200 clock cycles, the the sensor will send a new sensor, it will send a new master write to the CPU, rather, right? And then that's not exactly accurate. It's not every 200 cycles. It's after the sensor's been idle for 200 cycles. So in other words, the sensor will give the CPU 200 cycles to do whatever it needs to do in between its master writes to the CPU. Okay, and then the CPU will write its sensor data that it receives from the sensor to the storage device using a master write. So in other words, what this means is that the CPU will act as a slave when it receives the sensor data, but it will act as the master when it writes the sensor data to the storage device. So the sensor will be the master writing a sensor reading to the CPU, and then the CPU will become a master writing that sensor value to the storage device, to the flash memory. So this way the CPU gets to act in both the slave and the master role. However, all of the transactions happening here are writes. Well, no, sorry, that's not necessarily, that's not actually true, because the CPU does have to read, does have to do a master read operation on the storage device in order to read the number of pages and the Who Am I register. So which we're actually going to give you that code. And I'll talk more about that in a minute. Okay, so so one of the challenges here is that the Verilator, which is the software that converts the hardware designs that we're using here, the hardware designs being the I2C master and slave devices, or master and slave interfaces, as well as the sensor and the simulated flash. Those are actual hardware designs written in Verilog and in System Verilog. Those are being converted to C using Verilator, and then your code is written in C. So you're writing code that interfaces with Verilog, Verilog converted to C. And then when you run your program, you run the simulation executable. You're actually your code is interacting with a hardware simulation, essentially. The problem is that while Verilog and System Verilog support tri-stated values, meaning that you can have multiple modules that output to the same physical wire, that are connected to the same physical wire as an output. Of course, only one can write at one time. You can't double drive a wire, but whenever you have that situation and you have a module that is connected to a wire that is being driven by another module, you can write a Z value to that wire. So in other words, the idea is that you have tri-state output values. So I can have two modules driving the same wire structurally in the design, but during the time that the hardware is in operation, only one of them at most can be driving a 0 or 1 to that wire, whereas the other modules connected to that wire are driving a Z, a high impedance, meaning that they're kind of disengaging themselves from the wire when they're not in control. So this is what nominally would happen in I2C. I mentioned that the control of the SDA and SCL wires are changed depending on who the master and who the slave are, and also in the case of SDA, that the driver of that wire changes even during the course of a single transaction. That behavior is not supported natively by Verilator. So in order to simulate that, we had to complicate things a bit. So your simulated CPU actually has when it outputs to SCL and SDA, it does it through the SCL_I and SDA_I output. Okay, and likewise, the other devices on the bus also have a separate output for their SDA and SCL, and then all of the devices on the bus have an input for SCL and SDA, which are actually selected from one of the bus participants right through a multiplexer. So so what does this mean for you? Well, the only implication for your lab is that when you do a make waves, you will see in the waveform the SCL and SDA in your waveform, but you'll also see an SCLI and an SDAI. Now, whenever your CPU, your code, is in control of the either one of those lines, there'll be a matchup between SCLI and SCL, for instance. For instance, you can see the SCL during this sequence here. SCL underscore I and SCL are both identical. They're the same. Likewise here for SDA, I, and SDA. So what that means is that these are the CPU is driving the SCL and SDA during this time period. But if you look over during this interval, you can see that the CPU is outputting a 1 to SCLI, whereas the SCL has a clock signal there. Likewise, SDA looks different from SDAI looks different from SDA. So during this period, another device, the sensor in particular, is in control of the I2C bus during this interval because there's a mismatch. So, and then after that, then we have another period where the CPU is in control, as indicated by the match between the underscore I and the non-underscore I versions of both the signals. So, so this is, I mentioned this because I don't want this to confuse you. SCL and SDA are the actual bus. The underscore I version represents the output of the CPU, your simulated CPU. So again, if there's a match between those, if the CPU is in control, you'll see a match. If the CPU is not in control of one or both of the wires, then there'll be a mismatch between what the CPU is outputting and what you're seeing on the official bus, which is SDA and SCL. Okay, so so that's kind of a quick introduction to the lab. Now I want to run through the lab sheet here just to make sure that everything in here is clear. As I mentioned, the due date is April 28th. You'll be submitting your main.cpp as before in Lab 3. The simulated devices are now named VD004 and VD005. We changed the names from what they were in the last lab just to differentiate the differences in their behavior. But as I mentioned, VD004 is similar to VD002 in that it is a sensor, and VD005 is similar to VD003 in that it is a flash storage device, or that's what it represents. This paragraph mentions what I just described about SCL and SCL underscore I and SDA and SDA underscore I. So I say when viewing the waves generated from your code, you'll see traces for SDA, SDAI, SCL, and SCLI. The values of SDA and SDAI will always be identical, except during periods when VD004 or VD005 is actively driving that wire. So that's how the difference in those is when those two signals are different is your signal that someone else is in control. Now you don't have to do anything in your code to yield control of either one of those wires. The way we have it designed is that VD004, the sensor, has priority in the sense that when it wants to take control, it can take control of either one of the I2C wires. If it is not in control and VD005 wants to take control, then it then has priority, and then finally the CPU has the lowest priority. So what that means is that there is a fixed priority scheme, and the CPU has the lowest priority, meaning that if either one of the two peripherals here wishes to control either one of the I2C signals, they can do that, and they could. And if the CPU is trying to control the wires during that time, it will lose control. Okay, so keep that in mind. Now, from the perspective of your code, you're going to be using the IO read and IO write functions as before, but this time the only two signals that you can read and write, and you can read and write both, is IO_SDA and IO_SCL. So those names, obviously those signal names have been updated to reflect the I2C bus. Okay, so the sensor is VD004. It collects sensor readings that may contain between 1 and 128 bytes of data. It will begin collecting data once your design reads the number of page register from the VD005. So until that time, it'll just sit idle. After your CPU reads the end page register from the flash device, the VD004 will perform I2C master write operations to the simulated CPU every 200 clock cycles of after every 200 cycles of its idle time. When it's ready to send a batch of sensor values, it'll send n+1 write transactions to the simulated CPU. The first byte that it sends will be the number of sensor readings. So this is how your CPU will know how many follow-up bytes to expect for the current batch. And the next n transactions will contain the sensor values. So basically what that means is, like, I'll receive, for instance, a value of 4, which then will tell me that the next 4 master writes I receive from the sensor will be the sensor values associated with that batch. The I2C address of the simulated CPU, of your CPU, is 7A in hex. So when the sensor does the I2C master write to your CPU will be a slave, and it should expect the address during that transaction to be 7A. And it should only respond if it's 7A. Otherwise, it'll assume that master write or master read, but you should only see master writes. It will assume that that wasn't intended. That transaction was not intended for the CPU, right? So in other words, if I see an address that's not 7A, I should ignore it, because obviously that transaction was meant for another device. This VD005 is the simulated flash memory. The flash memory, as I mentioned, will use a simplified interface compared to the last lab. It will have 4 registers. It will have number of pages, end page. Now notice these addresses are different than what we use for I2C, but it has a number of pages, which it will return the number of pages available in the flash device to the CPU. And I just noticed that this should be read, right? Because you would be reading the number of pages. So I'll fix that before we post the lab. So just to be clear, that mode should be read. Page select, on the other hand, is the way to tell the storage device which page you're writing to. So that should be a write. I would be writing to that. So again, num page is the number of pages available in the flash device. Your CPU should be reading that. Page select is which page you want to write to, so your CPU should be writing to that register. The whoami is a signature, is an identifier, and the mode there should be read. right? So your CPU can read the who am I, and that should always return the value 36. This is a nice little test you can do, a sanity check. In fact, it's required that you read that in your lab, in your code. So that would be again a register that the CPU would read from the flash memory. And then there's a data register, and the CPU can write to that register to write a new to write a byte into the flash memory. So the sequence here is that I write a page number, and then I write the data register one or more times to write consecutive values into the page, into the page that I selected. Now I want to point out that in this lab you do not need to write the metadata associated with each page. You don't have to write the magic number or the page number as you did in lab 3. So you'll note that that's not required. Okay, so your program should the first thing it should do is query the who am I register on the VD005. It should verify that it returns the correct value. If not, then your program should display an error message in exit. The program then should query the number of pages on the VD005 to determine the capacity of the storage, because our objective here is to fill the storage to capacity, at least in terms of the number of pages the number of unique pages that we write. Reading this register on VD005 will trigger VD004 to initiate its reading of its sensor and sending its sensor values to your simulated CPU. You might say, well, how would VD004 know that we read a register on VD005? Well, it's a shared bus, so it snoops. The sensor snoops the bus, and it sees when there's a request made for a number of pages, even though that request is being made between two other modules on the bus. So the sensor is spying. At that point, your program should enter an infinite loop, waiting for a sensor value, which will come in as a master write from VD004. And the first byte that comes in that way will contain the number of sensor readings in the first batch of sensor readings. Then it should write it. At that point, after that transaction finishes, the CPU has 200 cycles then to write which page it wants to start writing on the flash memory. So be careful there, because 200 cycles isn't a lot when you consider the fact that each transaction is 18 cycles, and if, for instance, it's 4 core cycles per... Now, by the way, when I say 200 cycles in between writes from the sensor, I'm talking about the core cycles, or the simulation cycles. When you perform an I2C read or write as the master, you can define, however, how long each I2C bus cycle is, right? So you've got two different clocks here. You've got a core simulation clock, which is what you're referring to when you call the delay cycles function in your code. And I'm also using that same clock when I say that there is a 200 cycle delay between the sensor writing its sensor values, sensor values and number, and in the case also it sends the number of sensor values per batch as well. So those are the two clocks that I'm referring to. You'll notice, in fact, you might have noticed in my little screenshot for the waveform, you might have noticed here that the clock period during this phase of operation, which is where the CPU is writing to the flash, that clock that clock cycle time looks longer than this clock cycle time, which is when the sensor is writing its sensor values to the CPU. And that's fine. Obviously, the sensor is using a faster I2C clock than the CPU does during each of their respective masterships of the bus. So keep that in mind. Okay. Okay, so the top level operation is that your CPU will read the whoami register from the sensor, then it will read the number of, the whoami from the storage device, and it does. Your CPU does not need to read the whoami from the sensor, only from the storage, the flash storage. This is another difference from lab 3. So it reads the whoami from the flash device, then it reads the number of pages, and then it will receive the, at some point, it will have to just wait to receive the number of readings from the sensor, at which point it will write the page select, which will just increment from 0 up until the number of pages that are available on the flash device. And then it should then receive the first sensor byte, and then it will write that sensor byte to the flash. Then it will receive the second sensor byte, and it'll write that byte to flash, and so on. And then eventually it will have to move to the next page in the next batch of sensor readings from the sensor. Right, so you sort of have a nested loop. The outer loop here is iterating through each of the available pages on the storage device. The inner loop is iterating through each of the sensor readings in each batch of sensor readings that are to be stored in each page on the flash device. Okay. Once your program has exhausted the number of pages, then it will just exit. Right. So even though the sensor will continue to operate indefinitely, once you fill the flash device, there's no point in continuing to read those sensor values. So you can exit the program at that point. Okay, so programming environment is a little different from the previous lab. I mentioned that the pins that we're reading and writing are called IO_SDA and IO_SCL. You don't need to worry about dealing with NACs, which are failed acknowledgments that could potentially occur within a transaction, within any I2C transaction. Now, in order to simplify this lab as much as we can, we are going to provide you with most of the project code. We're going to give you the main function, which is what is implementing the behavior shown here in section 3.3. So kind of the top level design, the sequence that it goes through to read sensor readings and write them into the storage. So that's all contained in the main function. We're going to give you that. There's a function that is called from main that requests mastership of the I2C bus, which we call the master_I2C. That function, which performs either a master read or a master write on behalf of the CPU, for the CPU, is another function that we will provide. So essentially all of the interaction between the CPU and the flash is going to be done, is finished. It's in there for you. So what does that leave? Well, it leaves the slave the slave write transaction. So you are to implement the functionality for the CPU to read sensor values from the VD004 through the master write transaction. But to help you with that, we are also providing 3 macros. So there's a macro called wait for start bit, and there's another one, there should be wait for stop bit. Need to add that in there as well. I mean, it's in the code, it's just not in the handout. I will fix that before we release the handout. So there's a wait for start bit, wait for stop bit. Those are macros that will basically just keep advancing the simulation using, by one cycle at a time, doing a wait cycles 1 until the start bit or the stop bit, depending on which macro you call, is found. It is seen inside the, or has occurred, I should say, on the I2C bus. And then there is a wait for rising SCL and a wait for falling SCL, which allows your code to, in a similar way, wait for either a rising or falling edge of the clock. So you are to implement the slave underscore I2C. We also provide a skeleton for that function that has some comments that direct you on what to do, and then your code will then mostly just need to call these macros to be able to interact with the bus. And then the only other thing you need to do is take care of recording data that's on the bus. So you'll have to sample the SDA, for instance, when you're reading sensor data, and store that into a variable in the C code. So suggested plan of work. Read the comments in the code that we give you. There's a main.cpp file. It includes a lot of comments as well as placeholders to where you are supposed to insert your code. You then need to fill in the missing code in the slave underscore I2C function, because your objective is to implement that function. And then, as with lab 2 and 3, you can test your code with make simulation and run simulation, which will generate, like if you have print statements, any print statements you put in your main or in anywhere in your main.cpp will appear when you just run the simulation executable. So you can use print statements for debugging and for validating correct operation. You can also run the GDB debugger on the simulation, which is something that I do quite a bit. You can also make waves, which will bring up the waveform, and of course you can do a make decode to decode the I2C transactions, which I don't have listed there. There's also a make trace dump, which will flash dump, make flash dump, as well as a reference flash dump in there as well, for you to be able to validate whether things are working, just like as there was in lab 3, and I will add that information here as well inside the handout. So the grading rubric is the same as it was in lab 3. Basically, we're looking for correctness in terms of what data is stored to the flash device. We're also looking for good coding style, and a few other requirements, such as checking the Who Am I register. As I mentioned, we are not necessarily going to try to trick your code by issuing a knack or initiating a transaction, a master transaction that has the incorrect address. We're not going to do that. The behavior you see when you run the code, is the behavior that we'll be testing with. And of course, there's also a bug bounty still for extra credit. So I will also pull up the code just to give you just to give you a quick tour here. So this is the main.cpp file that you'll be receiving. We may make a few changes before we release it, but this should be more or less what you see. There's this SPI clock ratio 16, which obviously does not apply. That should have been taken out. There's a few defines here that I'll talk about more in a bit. The slave address is also defined as a constant. You'll notice that there is a type that is defined called I2C underscore transact. This is a C structure, or you can think of it as it's basically a C++ class where all of the members are public, and it's really just a package that you use to define what you want to do in an I2C transaction. It's also used to return data from an I2C transaction. So depending on which transaction is happening, which of the 4 possible transactions are occurring, some of these items inside this package may be inputs and others outputs, and which ones are inputs and which ones are outputs will change depending on the context. You will then see the 4 macros that I mentioned: wait for start bit, wait for rising SCL, wait for falling SCL, and wait for stop bit. You can see how those work, pretty straightforward. Then we have the slave_I2C function. This is the function that you are to fill in. There is a description of what the interface for that function is in comments. You've also got comments in there that tell you what you need to do. So for each one of these comments, you should have a few lines of code underneath there implementing the behavior as described by the comments. Then we have the master I2C function. You don't have to do anything for this at all. This code is complete. It should be working. There is a comment block above it that describe how you would use it if you were calling it. However, you're not actually going to be calling it because it is already called for you from the main function. So in the main function implements the top level behavior. We've got comments in there that describe what's going on, and you don't have to change anything in there either. So you don't need to change anything in main. You don't need to change anything in master_I2C. And so the only code you need to put in is slave_I2C. And even then, you're basically just writing the code necessary to implement the behavior indicated by each of the comment lines there. And even then, your code will then make use of these 4 macros that we've defined for you. Keep in mind, one thing that's a little confusing here I want to point out is that whenever you call one of these macros, even though they look like functions, and macros are typically in capital letters to indicate that they're a macro as opposed to a function. That's why they're all in caps. But the thing that's strange is that because these macros are sort of a self-contained block of code, you don't put a semicolon, or you don't need to put a semicolon after the call. So like if I wanted to call, wait for falling edge, I would say, I would just copy this and I would paste it into my code. You don't need to put a semicolon after it because this macro is going to be replaced by the block of code here, and the block of code that it's putting in already has all its semicolons. So that part can be a little confusing. So that's it. We're hoping that by implementing this function, even in the sort of guided way that we're doing it, you should have it should significantly cement your understanding of the I2C bus, at least for the on the slave side. If you have any questions, feel free to contact us, and we're available to help over virtual office hours. So thank you very much, and good luck, and I'll see you in the next lecture.